Welcome to the solutions to the Regents Physics Waves and Sound problem set, problems number 11 and 12. Number 11 reads, a sonar signal of frequency 1 times 10 to the 6 hertz has a wavelength, lambda, of 1.50 times 10 to the negative 3 meters in water. What is the speed of the signal in water? What's the period in water? And what's the period in air? We take a look at this. To calculate the speed of the sound in water is easy. It's a quick little V equals F lambda calculation. So V equals 1 times 10 to the 6 hertz times 1.50 times 10 to the 3 meters. And you get a speed of 1500 meters per second. I've added this diagram up here towards the top to help with the discussion on B and C. So to do the period in water, you would simply take the inverse of the frequency. And so shown over here to the right, your period would be the inverse of the frequency. So T equals 1 over 1 times 10 to the 6 hertz. So the period would be 1 times 10 to the negative 6 seconds. Okay, now for C, picture of a boat on top of the water. And what it's doing is sending a sonar signal down, which reflects off the bottom, comes up, and then refracts back out into air. And refraction isn't something that we've discussed yet, but that's what's going on here. And you can see clearly the speed of sound in the water being at 1500 meters per second. If we were to consider the air to be at its standard temperature and pressure, we know that that travels at about 331 meters per second. A little more than that if the air is warmer. But clearly 1500 to 300 and whatever is quite a difference. And what's happening here is the sound wave is speeding up due to a change in medium. And we call that refraction. We'll get into the bending of waves caused by refraction later on. You'll also be learning about that in your wave tank lab. But clearly what's going on here is that the wave speed is decreasing. If we take a look at a V equals F lambda analysis, one important thing for you to know, another important thing for you to know about refraction, is that all wave characteristics change during refraction except one. And that one that does not change is frequency. So the speed changes, the wavelength changes, the angle at which it enters and exits the boundary here between the two media changes, but the wave characteristic that does not change during refraction is frequency. Well, if frequency doesn't change, and it's the inverse, and period is the inverse of frequency, that means the period does not change either. So if the frequency in water leads to this period in water, period being 1 times 10 to the negative 6 seconds, then the period in air will also be 1 times 10 to the negative 6 seconds. Ask more about this in class if you're not sure or understand this discussion. Next, number 12, we have a sound wave of wavelength 0.70 meters, velocity 330 meters per second, produced for 0.50 seconds. What's the frequency of the wave? Pretty straightforward. Again, another V equals F lambda calculation. So 330 meters per second equals F times 0.70 meters. Divide, and you get a frequency of 470 hertz. How many complete waves are emitted in this time interval? Well, a frequency of 470 hertz means that 470 waves are being produced in 1 second. But we're told the time interval up here is half a second. So if 470 waves are produced in 1 second, if we took that and divided that by 2, we would get 235 waves produced in 0.50 seconds. And C, after 0.50 seconds, how far is the wavefront, the front of the wave from the source of the sound? This is simply a distance divided by time calculation. So V equals D over T. 330 meters per second equals D over 0.50 seconds. Multiply both sides by 0.5, and you get 165 meters, which to 2 digits would be 170 meters. That'll do it for our solutions to problems 11 and 12. More on these concepts as we do problems 13 and 14 together in class tomorrow.